Tendrán que gritar en Meet. Okay, so yeah. Okay, so we are moving on to a new topic, which is distributed data processing, specifically static data. So in terms of massive data processing, if we think about companies that have to process massive amounts of data, we might think about Google, for example. So, okay, we have this search engine, Google, that many of us use every day. Some of us maybe use something different, DuckDuckGo, or some other, maybe Bing. So how do we operate on this? Oh my God. How do we build this Google search engine is the question. So behind Google we have thousands upon thousands upon thousands of machines. Yeah. So we saw in the last class ORMI how we can communicate between different machines, and there are various ways, various protocols, and so forth. These machines that are connected via Ethernet, right? So recently, Metcalfe won the Turing Award, the Nobel Prize of Computation, for his contributions to developing Ethernet and his contributions to the internet and so forth. So how can we use machines to do this? So what do we need to do in Google? If we think about the processes that Google needs to implement in order to implement its search, what processes do we need to run? So the first thing is we have machines that have no data on them, they have nothing, right? So we have a lot of hardware but nothing implemented. So what's the first process, the first task that Google needs to implement? So it needs to get web content, right? It needs to get some pages from the web. What's this process called? Scraping is similar, yeah, but it's called crawling, yeah? So we need to do some crawling. So crawling is this idea of parsing links from web pages, scheduling links for crawling, and then downloading the pages and doing this recursively. Okay. Scraping is the idea of extracting data from web pages. A little bit different, but it's related. So what would we need to do once we have all these HTML pages and whatever content from the web? We need to somehow, if we just have them in files or in a data file, that's not going to be much good for search, right? So we're going to need to do what's called indexing, right? So we're going to need to extract some keywords from the web pages. We're going to need to index keywords to web pages. We're going to need to index the keywords. We're going to need to be able to create some indexes that are efficient and allow for finding web pages. Yep, and then updating those indexes. So the third thing we would need. Any ideas? Once we have crawled documents and indexed documents, what else do we need? We need ranking, right? So we need to say, okay, how good is this web page as a result for a certain keyword? How relevant is it to a particular keyword? How important is the page? How many users clicked it? What domain is it on, and so forth. So we're going to have some processes for ranking. And a bunch of other stuff relating to what advertisements to show for each search and whatever it might be, right? So the question is, okay, how are we going to implement these tasks over a massive amount of data, right? So we see that the volume of data that we're working with is huge. So we need to implement this on thousands of machines as well. Yeah, these processes. So this is a massive engineering task. So how do we implement all of these things on thousands of machines? Okay, so one option, let's go back. One option is we're all engineers here, we're all studying engineering. It's a huge engineering task. We could divide and conquer, right? So we could divide into 3 teams, and we'll say the left side of the room here is responsible for developing all the crawling infrastructure. You get together and start talking about crawling and how to implement it on these machines. The middle part of the room is dedicated to indexing. You're going to work on all the indexing infrastructure and how to implement it on the machines. This right side here, you're responsible for ranking. So what pages should be returned first for what searches, how do we measure relevance? And the people on Zoom or Meet are responsible for ... Okay, so they have to do whatever the other parts are. Would that be a good idea? Is this a good way to divide up the work? No. Why is that? Why would it not be a good idea?
Because if one stage has a very high overhead,
Okay.
that makes it slow.
So let's say the indexing were the hardest, then in this case you would have to work a lot harder than the other people, yeah? Even leaving that aside, so that's one point, yeah? There is another point why this would be a bad idea. What's the first thing you're going to have to do in each group?
Wait for the other person.
Maybe. The group work. No, so you'll probably have to start implementing. If you're given thousands of machines and given this job, you would have to start figuring out, how am I going to get the machines to communicate, right? How do I send data from one machine to another? How do I decide where to put the data, right? So you're going to all end up repeating the same jobs of trying to figure out data placement, communication, how to replicate data, where the data goes, right? So it would be better to have one team just to work on a distributed abstraction, a distributed system that is somehow common to all of these tasks, right? So this is the idea of avoiding this problem that if we were to implement every task separately, we'd have to re-implement distributed storage, retrieval, distributed processing, communication, fault tolerance, and then re-implement those again in every team, and you would have uninteroperable things that don't work together in each team, right? So we don't want this. So this brings us to the idea of building distributed abstractions, some sort of basis on these machines where we have some distributed system that forms a framework or a base for other more complex business-oriented tasks. So here I have some typical functions that we could consider implementing on the distributed system, like writing a file, reading a file, deleting a file, appending. So this is what a file system does, yeah? So the first thing we're going to talk about is Google File System. So the Google File System was described in a white paper. It's maybe 12, 13 years old or so, maybe older. So it describes essentially a distributed file system, and it was published by people from Google at that time, and described how they solved the first task, which is just how to manage files over thousands of machines. Yeah. So what is a file system, first of all? A file system is something like, here's Windows file system, where we have some data about the course. We have some, GUI, some graphical user interface in this case. You might have a command line, you might have whatever it is, but essentially it gives you a view to files that are on your hard disk that you can open, access, and change, right? So we might have access via GUI or via command line. What does a file system do? So a file system, first of all, manages somehow the data. It typically splits a file up into chunks of storage. It remembers where the chunks were stored so it can retrieve them later, right? So a good thing about why do we even split the data up into chunks, it becomes easier to manage. And we avoid this situation where we have one big file in the middle of our drive that splits the capacity on both ends, right? If we're only to store files sequentially. So splits up a file into chunks of storage. So in my machine, for example, it would be 4 kilobytes. If I create a file and I just put some characters into it, well, it could be 0 bytes for a while. But if I put in maybe about a kilobyte of data, it will still take up 4 kilobytes in my disk. Yeah, so the other 3 kilobytes are wasted. So you'll see file on disk sometimes. So this would be NTFS, New Technology File System. Unix uses something similar, and so would Mac. So you have these little blocks, and maybe some people remember from old days defragmenting hard drives. Maybe not, maybe so. But this was used to reorder the blocks so that those that were accessed more frequently together would be in the same part of the disk. Yeah, so I don't think anybody bothers to do that nowadays. So these would be 4 kilobytes blocks, 4 kilobyte blocks. Second thing a file system does is it organizes a hierarchical directory structure, right? So it gives you directories, subdirectories, files in those directories. Yeah. So we see this sort of hierarchy of documents from the root of the drive to the files. Next, it tracks file metadata. So size of the file, the data was created, the data was last modified, who owns the file, who has permissions for the file, locks, is someone using the file currently. So we see, if we look for more details, we can see who the owners are, when it was created, when it was last modified, and so forth. It also provides read, write, update, and delete interfaces. So we can essentially, so we can open a file, we can write a file, we can open a file, make some changes and save it, or we can just delete a file, for example. Yeah. So this is what a file system should do. So then the question is, what does the Google file system do? It does pretty much all of these things, but it does it over thousands of machines. Yeah. So it does the same sort of thing. Yeah. So this is what we need to implement on hundreds or thousands of machines. So which architecture do you think Google uses? The last time we spoke in the distributed systems class, the kind of overview or introduction class about the client-server paradigm and the peer-to-peer paradigm and contrasted them. So which do you think Google uses? Peer-to-peer, okay. So in truth, what it uses is somehow more of a mix between the two that I like to call client peer to server to peer server client. Yeah, so it uses a mix of both. There's no real, in some parts it's peer-to-peer, in some parts it's client-server. Yeah, so we'll see how that works soon. So there are some main assumptions if we were to think about designing something like Google File System from scratch that we have to take into account. The first thing is that files are massive. So typically we're going to have a crawl of the web, and we're going to have files that are maybe terabytes large, or maybe even petabytes in size. Yeah. So we're not going to be working with small text files. Yeah. Because there would be too many. In general, file systems are not a good way. If you're ever working with lots of data, the worst thing you can do is store lots of small files. Yeah. You want to gather them together into one or several big files. Yeah. You don't want thousands of files or millions of files in your file disk on your file system. So files are huge. Yeah, so we have a very large TSV or CSV or binary or JSON file. Whatever it is, it's massive. Yeah, it's a terabyte. Okay. So files are often read or appended. Yeah, so we're not going to open a massive file and edit 5 characters in the middle and then save it. Yeah, this is not some operation. You can kind of do that in Google File System, but it's not the intended application. Yeah. So we're dealing with data in batches. Yeah, if there are changes, they will come in the next batch. Concurrency is important. So as we mentioned, we have different teams who need access to maybe the same data, like which pages link to which other pages. So we need to be able to handle multiple users using the file system at the same time. Failures are frequent because we have so many machines that it's quite likely that one hard disk will fail every day. Let's say if you have 3,000 machines, about on average one hard disk will fail a day in those machines. And streaming is important. So it means that we're never going to load an entire file into memory like my machine does or your machines do. Rather, we're going to be reading document by document or line by line. We're never going to be able to load the entire thing into working memory to open it in an application. So how should Google design its distributed file system? That's the question. Yeah. So let's have a look at that. Let's try to answer that question and see. So the architecture that Google went for is to have essentially 2 types of machine. There are chunk servers, which are those machines that will store the actual data in the file system. And these chunk servers have the storage, yeah, that we see down here. Okay, and then we have a master machine. And this master machine is somehow in control of managing the state of the file system. Yeah, so we could say this is something like a server. Yeah, in the client-server paradigm. However, it only manages the metadata. So we have in the master, in memory, in RAM, to make sure it's very efficient access. We have very efficient access to the state of the file system. We have details about what file, what blocks are where. Yeah. So some assumptions we have. The first assumption that is really strange, that would be a disaster if we applied it to our machines, is that there are 64 megabytes per chunk. Yeah. This would be a terrible idea if we were to use this on my machine. Why? What would be the minimum size of a file on this file system? It means that the smallest file, no matter how small, will be 64 megabytes. Yeah. So if you store a couple of letters in a text file, yeah, it will weigh 60. It'll have 64 megabytes in size. Yeah. So terrible idea for our local file system. Great idea for Google File System. Why? Because files are massive. Yeah. So we have 64 megabytes per chunk, and we have a 64-bit label for each chunk. pretty common in file systems to work with longs or 64-bit identifiers for blocks. Yeah. Sometimes the integers are used, but typically it's longs. So we can already calculate a theoretical limit. Every file system pretty much has a theoretical limit for how much data it can store. Yeah. In this case, it would be we can have 2 to the 64 times 64 megabytes. Yeah. So it's quite large. Yeah. So we have a theoretical limit for how much we can store here, and we're going to assume a replication factor of 3. Yeah. So this is a pretty common assumption to have 3 copies. So if there is a mistake in one, an error in one, we can use the other 2 to solve the error, right? If we only have 2 copies of something and one of them is wrong, then we have a tie, right? Because we have the wrong version and the right version, and we may not know which one it is. Okay, so we have now a client who would like to write a file. Yeah, someone, maybe the crawling team has gathered some data and they want to write the file to the distributed file system to share with everyone across Google. Yeah. So we're going to apply what's called pipelined writes. What are pipelined writes? The idea is that the client has their file, blue.txt, full of lots of interesting data. It has 150 megabytes, which will mean that we'll have 3 chunks, yeah, 64 megabyte chunks. So 64, 128, and then we'll have a third chunk that uses only 22 megabytes, but it will still take 64 megabytes of space. Yeah. So the client sends just the metadata to the master. Yeah. Only just says, this is my file name, this is where I want to store it, this is the directory I want to store it in, this is the size, right? And the master says, okay, understood. Sends back some information to the client. So the client then is told to send which chunk to which machine. So the client is told by the master, send chunk, the first chunk to A1, machine A1. The client sends the data directly to A1, and A1 sends it on to other machines to make sure it's replicated. Yeah. So the client can also sends, let's say the master says, let's store the second chunk on B1. It sends some data about what machines are going to store that data, so A1 and D1, and then the client sends it to one of those machines, and that machine copies it onto the next one. Yeah. So now we have the 3 blocks written, right? So why do we do it in this way? So why does the client not just send all of the data to the master and say, store this for me? And the master then chooses which of the chunk servers stores the data and sends it to them. So why not just send the data to the master, and the master then decides how to split it on which machines to store it? So as we see here, we only exchange the metadata with the master. What the file name was, how big it was, and then the master said, okay, we're going to store this on these machines, right? So why not just send all the data to the master and let the master take care of it? Why are we sending the data to the individual chunk servers from the client? Yep. I'm sorry, so the question is, okay, we could send the data from here, from the client to the master, and then the master will divide it amongst these machines here. We've not done that. What we've done is that the client exchanges some messages with the master, and then the client sends the data directly to one of the machines. Yeah, it's a bit more complicated what we've done. So it has a benefit. And the benefit is that we don't have to send all of the data of the entire file system through one machine. Yeah. So the benefit is that we do not have to send the entire data through the master. Yeah. There isn't one single point. So we still have to store the metadata and all of that with the master, but we don't need to send all of the data, the massive amounts of data through one machine that could become a bottleneck. Yeah. So we have the benefits, like we saw in the second class, of a central directory. We have one machine we can ask to find out where something is stored. Yeah. However, we need to minimize somehow the work it has to do to avoid it becoming a bottleneck. So let's say the client had a second file, orange.txt. can again notify the master. The master gives some information to say, okay, we want to store it on these machines. The client can send the data to any one of those machines, and that machine will then send it on to the next machine and to the next machine. Okay? And so on for the second block. Any questions or doubts about that? No? So again, here every block is just a copy. So we have first block of blue, we have 3 copies. Second block of blue, 3 copies. 3 copies of the third block of 3, and for block 1 and 2 of orange. Yeah. So we have 3 copies of everything. The data never goes to the master. Only the metadata, the information about the file size and so forth. Yes.
Why is it 3 copies?
So in general, we define that. So you can say in your file system, I want 1 copy, or I want 2 copies, or I want 3 copies. So the idea for 3 copies would be that if something fails, that you still have 2 copies left, right? Why not just 2 copies? So the problem is if there's 2 copies and both of them disagree, you don't know which one to trust. So 3 copies gives you tolerance to 1 Byzantine failure. Byzantine is this idea that they don't agree. Yeah.
But in each storage are the 3 chunks or the 2 chunks. Every copy has the number of chunks that the person gives to the master?
Every person is in the client here. So this client would be, it's an unfortunate name, but they call it a fat client. So it means that this client is part of the system as well. So it's not like a web API or your browser calling a server. This client somehow has implemented the functions of the Google file system. This client doesn't have information about the overall state of the file system, but it has the ability to contact the master of the file system and retrieve that information from them. Yeah. So so this client here is not like a thin client. It's not like just something that makes a request. It somehow as well has some code for the file system. Yeah. Is that okay? Fault tolerance. What happens if a machine fails? We quit our jobs and leave? No. So we need some sort of way to detect when there are problems with the machine. So the master is constantly communicating with the chunk servers just by sending them like a ping. Yeah. Are you still awake? Are you still working? Yeah. If it detects that there is a machine with a problem, for example C1, what do we need to do? We need to respect the replication factor. So all the stuff that was on C1, where we had the first block of blue and the second block of orange, we need to copy this from somewhere else. Yeah, so we need to get that from somewhere else, and we need to sorry, something is not going forward. Yeah. So we need to copy those chunks to other machines. Yeah, the ones that are still alive. So what does this mean? It means that the master machine here has to choose, as you see, some new replications for what was previously on C. Yeah, and then it will tell one of the machines that has a copy of that to send a copy to another machine. Yeah. So in this case, E1 sends to D2 its copy of the second block of orange that was on C1 previously. Okay. So in terms of reading, again, we have the same choice, right? So how should we read data through GFS? So one option is that the client sends a request to the master and says, I want to read blue.txt. I want all of the information from blue.txt, right? And then the master would ask the chunk servers for the data and then send it back to the client, right? But we don't want that. Why? We don't want the reads, all of the reads to go through the master, right? So rather, the master will tell the client, here's where the data are. You can read the data directly from there, called direct read. Yeah. So we avoid this bottleneck of sending all the read data through the master. So the client asks the master, hey, I'm looking to read blue.txt, and the master says, oh, you can read it from any of these machines here. The client can then go and read from any of the machines that has each of the chunks, one of the chunks, and read the entire file. Yeah. So again, the data will be read directly from the client, yeah, not through the master. We don't want a lot of data to go through the master. So Google File System also has something called primary replicas. It does allow for changing blocks, so it does allow for edits in the middle of a file, but it's not really optimized for that. This is not a typical operation, but if we wanted to do it, we could. For this, Google File System needs to maintain what are called primary replicas. These are the replicas, the chunk servers, that are in charge of a particular block. Yeah. So these chunk servers are the ones who hold the lock. They say, oh, there's, somebody else is editing this part of the file. You can't do that at this moment, for example. Yeah. So every block has a primary replica, which are the ones that are underlined here. Yeah. So it chooses somehow, the master will choose them arbitrarily, but to make sure that things are balanced, right? So the primary replicas are balanced across the machines. So the client says, I want to change the second block of blue.txt. The client gets the information about what the servers are with those chunks, and also the information about the primary replica, that it's B1. So the client specifically has to request a change to B1, yeah? But first, it can send the data in any order at once. So in this case, it sent the data to D1, and then D1 sent the data to A1, and then A1 sent the data to B1. This is something called staging. That's a very common concept in distributed systems and other systems. So we've just gotten the data ready on every machine, but we've not done anything yet. The data are staged, yeah? So we've not actually called commit, yeah? So we prepared the change, and then the client must request the commit to B1, to the replica, the primary replica, to the main machine. Yeah? So once B1 has done this, then it asks A1 to commit, and receives the acknowledgement from A1, must send the commit to D1 and receive the acknowledgement from D1, and then it can acknowledge the client. Yeah. So we don't really care how the data are shared. It can be shared in any way, but the commit message has to go through the primary replica because it holds the control of what happens to that chunk. Yeah. So having one primary replica avoids a case where there's a second client here that sends a commit message to D1 with a different block, right? So somehow in the system, only one chunk server can accept a commit. Does that make sense? So we avoid the problem of parallel writes, where we change the block in two different ways, yeah, by having a primary replica that holds the lock. Does that make sense? Questions? Preguntas? Dudas? No? Okay. So this is the control, this is the flow again, where the data, it doesn't really matter. The client can send it to whatever chunk server they want that has a copy, has a copy of block 2. They will share it amongst themselves, but the key thing is that the commit messages need to go through the primary replica to avoid parallel changes. A couple of more advanced features, and then we're done with GFS. So one thing to note is that in these large buildings with thousands of servers, typically we have racks, and then we have units in those racks, and then in each rack, this is a rack here, this is another rack here, possibly this is another rack here, there's some sort of switch, rack switch, yeah? So what could happen is that we could lose a rack switch, in which case we could lose an entire rack. So these rack switches would be a single point of failure for that rack, yeah? So if this happens, let's say we have 3 racks like this, yeah, and we have these rack switches. Then we have these core switches that allow for communication between the racks. Yeah. So this is all well and good, but if we have a problem with the rack switch, we're going to lose access to that rack. Yeah. What does that mean? It means we need to be a bit careful when we do replication. We don't want all copies on one rack. Yeah, because now there's a single point of failure, which would be the rack switch. So rack awareness is this idea of telling the file system about which machines are on the same rack. And what it can do is make sure that there's copies of every block on at least 2 racks. Yeah? So essentially, we tell the file system, the master knows not just what parts of what files are on what machine, but also which machines are on which rack. And based on this, it can avoid sending the same block to 3 machines on the same rack. Yeah? So the most common setup here is to have 2 copies on the same rack and 1 copy on a different rack. So this gives a balance between efficiency because the communication within a rack is more efficient. It's easier to have 2 copies. And fault tolerance, right? So we have a copy on another rack if we need it. Okay. So some other operations, GFS also allows for rebalancing, which I'm not going to get into too much detail, but the idea is to rebalance the storage, especially useful if new machines come on and you want to start using them. Deletion. So the idea of deletion, a very common theme as well in these sorts of systems, is that we're not going to delete it straight away. We're just going to rename the file, to some hidden file, and it will be there, and that's essentially a recycle bin. So if somebody wanted to undelete a little while later, they could do that. Yeah, it's still there, it's just not visible. And if we need the storage or after a certain period of time, we can just delete that file to recuperate the storage. Yeah. So there's also some work around monitoring stale replicas, which is what happens when a machine that had a copy of a block goes offline and then comes back online but with an older version of the data. Yeah. So essentially the master needs to keep some version information about when changes were done to each block. Yeah. So I won't get into too much detail on that, but you can have a look at the white paper mentioned at the start if you want to see more about that. So let's have a look and see what do we think are the main weaknesses of GFS as we discussed. What would you see as the main problem with GFS? The main weakness?
It's not very efficient.
Not very efficient, okay.
Memory, in storage terms, like we store the same things that, okay, give us redundancy, but efficient in storage.
Okay, so you say that a weakness is we are keeping 3 copies of everything, right?
No.
You know?
But and it's like a balance thing. Like, yes, we get redundancy, but we store the 3 same things, and I don't know. And if it's like 1 terabyte file, we have
3 terabytes. Yeah, exactly. Yeah. So that's what I mean by weakness as well. In that it's not something that's like bad. It's something that you use to trade off for something else, right? So it's a valid weakness. Yeah, you need to keep 3 copies. So in GFS though, that's a setting. So if you wanted to disable that, you could. It wouldn't be a good idea, but so it's not essential to GFS, that part. But yeah, but there is something that's more central to GFS. No pun intended. That's a problem. Which is the master. If the master fails, your Google file system, no matter how many thousands of machines you have, the whole thing doesn't work anymore, right? So the master is a single point of failure. So how can we get around this? We can do like RAID hardware replication. Yeah? So we can try to somehow have 2 machines that do exactly the same thing. Yeah. We can also, another problem with the master is that all of the data are in memory, which is volatile memory. So we need to have some sort of transactional processing. So we need to have logs of what's going on to be able to restart the machine in case of a problem. So we can have logs and checkpoints. So we.
Sorry, what if we have a master that checks on the master and vice versa?
So there is a similar notion in Hadoop. There is a secondary name node. So there are different kind of roles that can be associated with the master. There can be one that, for example, that doesn't do the master, but does take care of the logs and checkpoints, and could, restart the master if necessary. So there are different ways of getting around this, and it could also be a secondary master that does some administration or paperwork for the master, for example. Yeah. But a typical thing to do is use a more powerful machine. Lots of RAM, lots of cores, somewhere in a central part of the network or whatever it might be. Yeah. So the master node is also a bottleneck, right? So in this case, as I mentioned, use a more powerful machine so that it can process all of the requests coming, and we want to minimize the traffic, the data we send through the master. So for this reason, we have the direct reads and the pipelined writes. We don't pass any of the data through the master. It all goes to the lower level chunk servers. So the master node metadata needs to be kept in memory, and each chunk needs 64 bytes to address. Each chunk needs 64 bits to address. Sorry. Shouldn't it be bits? I think that should be bits, I'm pretty sure. So in any case, we have a limit to the amount of data we can store because we need a certain amount of memory in order to be able to address the data. And we need to, no, I guess it might be 64 bytes because probably it's not just the chunk ID, but it will also be where it's stored. So no, sorry, 64 bytes. It's each chunk has a 64-bit identifier, but there's more data we need to store as well. That would just be only a part of the address. So each chunk needs 64 bytes to address, and the chunk data can be queried from each chunk server. So it means that every chunk server as well maintains a copy of what chunks it's storing. So it has some local information to help take some of the work off the master node. Of course, if we had very small chunks, like if we had 4 kilobyte chunks, like I have on my machine here, this would not scale very well. Yeah. So if we want to work with massive amounts of data, the idea is with larger blocks, we can store more data and take some of the load off of the master. We have fewer blocks to manage. Yeah. The trade-off is that the smallest size of a file on your file system will then be the size of that block. Yeah. So larger blocks means, okay, it's useless for working with small files because even the smallest file will be 64 megabytes. But it means that the master node will have to manage or address fewer blocks, creating a larger capacity overall. So that's these are the weaknesses of the Google file system. Any questions about something here? They got away, I guess. Any questions? Any doubts about this part? La segunda acá. Yeah. So the idea is that es como bottleneck de cuello de botella, ¿cierto? So it's like essentially the master node somehow has to receive all of the requests coming to the distributed file system, has to process them, and it has to do the metadata. So in the Google file system, we've tried to minimize the amount of stuff that goes through the master. So it would be much worse, for example, if we sent all of the data through the master to share with the chunk servers, because then all of the data of the file system has to be streamed through the master. And that would be that would be much worse as a bottleneck. But the master node is still a bottleneck in that it still needs to receive all of the requests from clients that manage that file system. So it still needs to manage the metadata. It's a lot better, but it can still be a bottleneck. Yeah. Okay. Questions? Nope. Okay, Google File System. We just spoke about Google File System, but you're never ever going to use a Google File System. Yeah, because it was proprietary and internal to Google, so why did we do that? The good news is that there is an open source version of Google File System, HDFS, Hadoop Distributed File System, that's been around for well over a decade, I guess, well, about 14 years or so, but it's still commonly used today. So this is an open source version of the ideas we saw, which are proprietary and internal to Google. Google is probably no longer using Google File System. So we have also some sort of translation guide. It's the exact same concepts we saw. They took the white paper, they implemented it in open source in Java. There are some names that are different. So instead of a chunk server, we use the term data node, and instead of a master, we use the term name node. So it's exactly the same idea. It's just an open source implementation of the white paper of Google. Yeah. So you will use HDFS. What we've done with HDFS or GFS is we've implemented these distributed abstractions here, which is write a file, read a file, delete a file, append a file. Okay. This is pretty useful already. This would be useful to the crawling team, to the indexing team, to the ranking team. But maybe we could identify more types of processing that is in common and define abstractions for that in the distributed setting. Maybe we could be a bit more ambitious with our distributed abstractions. Yeah. So this is HDFS, GFS, and then the question is, could we do more? Could we have more abstractions that are useful to everyone? Yeah. So something that's useful to all of the teams here, for example. Yeah. So essentially all we've done thus far is implement a file system, yeah, the kind of basic stuff. So in comes Google's MapReduce. So this idea was kind of, how would I say it? This idea wasn't super new, but when Google put a name to it and they essentially formalized, or they put down on paper how they're doing all the processing, it became an extremely popular idea, this idea of MapReduce, which is basically a mix of divide and conquer and functional programming, we could say. So there's a white paper. Again, Google, for whatever reason, I guess they felt that it was useful to share with other companies or with humanity or whatever. They wrote a white paper detailing what they were using internally to process lots of data. Yeah? So before we get into that, here is you. This is you. We're going to forget about MapReduce for a second and take a task. We have some workers, worker 1, 2, 3, and 4. And we have some sort of distributed file system. So you're basically the master of the distributed file system. You're the one who coordinates, the coordinator of this distributed file system. What we have is, I don't know, thousands of cards, playing cards. Yeah? And what your job is to coordinate it such that the distributed file system outputs for every type of card, like 2 of spades, the exact count in this bunch, this random collection of playing cards. So we see that there are 391 times 2 of spades, 192 times 3 of spades, and so forth. So how would you do this? How would you coordinate this distributed system to be able to count the cards as efficiently as possible? We'll assume that you and the workers are pretty reliable, in that given a task, you won't make mistakes. Yeah? Your machines.
One main approach is divide the work, the cards into, how do I say it?
Chunks.
No, but with aces,
No,
cards,
the suits, sorry, yeah.
Yes, I divided into suits. That's a main approach.
Okay, that's interesting. So you say divide the cards into suits, right? But you would have to take quite some time to do that, no? Who does that, right? Somebody would have to do that. Yeah. So who's going to divide it? So the idea was to divide it into suits, so that we have worker 1 maybe counting hearts, worker 2 counting diamonds, worker 3 counting clubs, and worker 4 counting spades. Yeah. So who divides it, right? Is the question. How do we do that division? So any other options? Any other ideas? Now we can talk about the different ideas then and compare them. See?
If you distribute the number of cards between all the workers, and maybe yourself, you get to the small structure and after everyone ends the count, they report to you and you somehow count.
Okay, cool. So we'll take all the cards, and we can do this with a file as well. We just kind of evenly separate them into 4 or 5 piles, depending if we include ourselves in the count. Yeah, and then we all count the cards, and then we take the final sums, and then one person, probably you as the coordinator, sums the totals and then reports the final output, right? So which is better between the two? So these are the two main directions we can consider. One is to partition first based on a particular suit, yeah, or whatever partition it could be. Sorry? Yeah, some criteria, yeah. So we could do a hash and take the last number or whatever, yeah. And the other one is to partition the very cheap way, which is just split it into 4 parts, send a part to each worker, and then let them count, and then see. So what's the benefit of your approach versus the divide the 4 chunks of cards and then spread them immediately? There is a particular benefit of splitting it by suit, for example, first.
So I know what worker is with which suit.
Yep. So you know.
What are they doing?
Yeah, so you know which worker is, what each worker is somehow associated with, what work they're doing. Yeah, there's I guess if you trust them, you probably won't need to know. So if they were black boxes and you assume that they're going to do their job, it could be useful in some scenarios, but there's a much bigger benefit to your approach. So the last step here is to do the sum, right? But in your approach, I see. So we can talk about that. It is we have to be very careful about how we partition, right? So it could be true that the work balance is bad if we choose a bad partitioning. If we assume here that somehow they're random cards and there's lots of them, we should be okay, because we should assume an equal distribution by suit. But if that wasn't the case, it could work out quite poorly in this case. Yeah. Whereas in the other case, it wouldn't work out poorly, because we're just taking a quarter of the cards and giving them to each of the workers. Okay? Yeah, so this is the major benefit of the partition by suit approach, is that we don't need to do a sum. There's no final aggregation. So each worker can do its own work independently, and then it can store its own chunk. Imagine a very large file. It can store its own chunk of the output, and the union of those outputs would then be the output of the overall process. Yeah. So in this case, it's debatable. Yeah, because there are only 52 types of cards. Probably the first approach would be better. But if we had to count more things, if the output was larger, it could be much better to go for the partition approach. So in general, the one that's favored by MapReduce is the partition approach, where we don't need to do a final merge of the output onto one machine. Yeah. So the idea is that we're going to partition the work. So we're going to somehow, based on some key associated with the inputs, in this case it would be the suit, we're going to associate inputs with a particular worker and allow that worker to process all the inputs that are similar to that. Okay, so how can we do a distributed word count? So let's talk about machines again, but it's the same idea. We could count again parts and memory on different machines and merge. That would be similar to the idea of just splitting a file into 4 parts and then dividing them. But if the data don't fit in memory, then essentially every machine will run out of memory. You won't be able to count the memory, because every machine will probably encounter a similar number of unique words. The dictionary size will be somehow larger in this way. We also have the problem of how to do the merge at the end. We need to sum the counts for the words across the machines. So what we could rather think about doing is counting parts on the disk on different machines and merging. Yeah? So again, there's a question of how to do that merge. If we just split a big document like we saw in Lab 1, for example, in 4 chunks and count the words of the 4 chunks on 4 different machines, we're still left with the problem of merging the final counts, summing them. So the way that MapReduce views this problem is to rather pre-partition the data. So the idea is that we're going to have some input on a distributed file system. Let's imagine it's a very large collection of documents, maybe 100 or 1,000 times bigger than what we saw in Lab 1. So we're going to have that in different, well, okay, here it's only 3 chunks, so it'd be a similar size to what we saw in Lab 1. But we're going to first partition the data. And here I'm going to define some sort of partitioning that is very rough and ready, as we say, just for the example, for the moment, which is I'm going to say that A1 is responsible for counting all the letters, all the words that start with a letter between A and K inclusive, B1 between L and Q, which seems to be very little, I think, maybe, and then C1 between R and Z. Yeah. So we have some sort of responsibility for each machine, like we did with the suits for the cards. Then we're going to have a distributed sort and count, where we're going to essentially on the disk sort the data and do all the stuff we saw in Lab 1. Yeah, so we sort it on the disk, assuming it doesn't fit in memory. We're going to sort it on the disk, and then we're going to count, run over that sorted list and count, and then output the data like this. So the benefit of this approach again is that here on this machine already we'll have the final count for a word like label. Yeah, we don't need to sum label across different machines. So with the pre-partitioning step, we have the benefit of being able to have separate independent outputs whose union address is the full output. Yeah. So again, whether this is better than the other approach depends on how large the output is, yeah, relative to the input. So in the card counting case, probably easier to merge after, right? If we have more inputs, probably better to partition the input. Any suggestion for a better partitioning than this weird letter thing I came up with? Rather than using the first letter. So we could, what we need is essentially some function that will take a word and give us a number between 1 and 3 or 0 and 2, doesn't matter. Between 1 and 3, and does so in a deterministic way. So if we receive the same word twice, we'll get the same response, but has a fairly equal distribution across the words. Right? So what we can do, for example, is we can apply a hash code to the word, and then take the modulo of m being the number of machines, which would be 3. So we take a hash code, we produce a long or an integer, whatever the format is, convert it into binary if it's not a number, yeah? And then we modulo that with the number of words. What is modulo? It's the remainder of the division. So 5 modulo 3 would be 2. Yeah? So 3 divides into 5 once, and it leaves 2. So we get the remainder 2. So this will give us a reasonable partition function that doesn't rely on, knowing the distributions of first letters or whatever it might be. Yeah. Of course, if we have some words that are way more popular than others, which does happen in language, we will have a bit of load balancing problems. Yeah, like de or la or el in Spanish. Yeah. So these may create some load balancing issues. Okay. So to understand MapReduce in more detail, or any questions or doubts about this? This is the core idea of MapReduce, which is one of the core ideas as well of Spark. So this is kind of one of the most important ideas in the course. This particular way this works. Yeah. So okay, we're talking about word count, but we're going to generalize this in a minute to much more general types of tasks. Yeah. So this is MapReduce. So again, I would say this is kind of one of the most important parts of the course. So if you have doubts, let me know. This will carry on for Pig and for Spark, and will be used in various other lectures later. So MapReduce. Essentially, we can break MapReduce down into 7 phases. We have an input, map, partition, shuffle, merge sort, reduce, and output. So the benefit of MapReduce is effectively all we need to do for whatever task we want to solve in MapReduce. We want to define the map function and the reduce function. And we can use this for counting words. We can do it for doing relational style queries, for doing joins, for doing group by count. We can do all sorts of tasks with this MapReduce framework. All we'll need to specify typically is the map and reduce functions. So let's see how this works just for the counting words example for the moment. So we have some input, which is a file with some words. Yeah, so we have this very interesting file. Pero sé que decir que la que said. Very interesting. Okay, so we have our input, and we're going to assume it's in 3 blocks. Of course, the blocks would be much larger in practice, but it's in 3 blocks in HDFS. Yeah, so every machine somehow has some data stored on it. So what's the first thing we're going to do? We have these 3 machines, and we're going to use these in MapReduce to count the words. The first thing we're going to do is a map. And what we're going to do for the map is we're going to create key value pairs from our input chunk. Yeah. So the keys in this case would be the word, and the values would be 1. Yeah. The values we don't actually really need to use so much here. They have a benefit that we'll see in a moment. Why 1? We don't really even need the values here, but they will be useful a little bit later when I talk about an optimization. So the next thing we're going to do is take this local stream of key value pairs, and we're going to partition them. So on each machine, we're going to create a blue file for the blue machine, a red file for the red machine, and a green file, although empty here, for the green machine. So this will receive all of the pairs where the key's partition is blue. So if we run the hash function and it gives us a value of, let's say, 1 to 3, if it gives us a value of 1, then it will be in the blue file. If it gives us a value of 2, it will be in the red file. If the hash modulo 3 of the key is 3, it will be in the green file. Yeah. So we assign each key value pair to a different machine. Next, we're going to apply a process called shuffle, which is a very bad name, if you ask me, but okay. Because shuffle in general means something random. When you do it to cards, it means randomize. Here, it's not random. You send but you are shuffling the data over the network. Yeah. So basically, it means that you're going to send data over the network. So you're going to send all the bits of blue files from each machine to the blue file. You're going to send all the bits of the red file to the red file, and you're going to send all the green bits to the green machine. Yeah. Next, we're going to do a merge sort. So we're going to, something very important to mention, sorry, here, is that although this is the only case you see it in here, all of these red chunks will be sorted. So when we're writing these files, what we're doing is, like we saw in the first lab, we're creating batches of data. Yeah, so we have some batch size, and we store a certain number of pairs in there, and when it fills, we write it to the disk as a red file. Yeah, and then we start another red batch. So all of these batches here will already be sorted. Yeah. So what we do then is apply a merge sort, and this gives us an iterator of all of the keys and values in sorted order. So we apply the exact same merge sort that you implemented in lab 1. Yeah. So this gives us an iterator. We can read over the data. Yeah. And in order to read over this iterator, we just need to have one line or one pair from every file here. Yeah. So this gives us an iterator over the sorted list of all of the pairs on that machine, and then once we have that, we can just, for every key value, we can essentially, for every key, we can group all of its values together. And then we can apply an aggregation. We can count how many values there are, what's their sum, what's their average. We can create pairs from all of those values, right? So in this case, for every key here, we group all of the values, which is easy to do when we read the data in sorted order, right? So we have this iterator over all the sorted pairs, and then we just group for each key all of the values. And then that will become, then we have to define a reduce function. So we have to define what we do here. In this case, we're going to say sum or count. It's the equivalent. The sum of ones or count of ones gives you the same results. And we get the final result here. Yep. So then we can output that to HDFS or whatever we want to do. Okay, does that make sense? Yeah. So probably one of the most important slides of the whole course. I'm not over exaggerating that. I'm not going to say that for every class. Yeah, so this combines ideas we saw already in class 1 and lab 1 of merge sorting external sorts, but doing it in a distributed setting, combining it with partitioning. And then what we have to tie it all together is this map function, which states how to create key value pairs from the input, and the reduce function, which says for every key, how do we combine all of its values? And we're going to be able to implement lots of tasks using this framework. Any questions? I don't know, I guess maybe it comes from distributed file systems, this idea of shuffle. I've seen it in different places, but for me, shuffle means random. Whereas here, it's not random, but it means kind of spread data on the network. Like, yeah, distribute, yeah, exactly, yeah. Or send, or I don't know, share. But shuffle, it's not just used in MapReduce, it's used in other settings as well. Yeah. Yep, couple of questions, yep.
How do you say on the color?
How do you?
Decide on the color?
So the colors would be based on this function here. So we'll say this is maybe machine 1, 2, and 3. And so we use the hash, we use this sort of function will be the default. So we take the hash code of the word and then we do a modulo 3. Yeah, and then that would give you a number 0, 1, or 2. Yeah. Same question. Yeah. Okay. We can change that if we want. If we wanted to override that function, we can do that. That's no problem. Okay. Other questions? No? Again, just to note here, the sort, so all these chunks are sorted, so when they arrive here, we just apply the merge sort we saw on the first lab. Okay. So there is a combiner. Yeah, so let's go back here actually 1 second. Does anyone see maybe something that's a little bit inefficient in what we did here? Anyone see maybe a possibility for optimizing maybe a little bit around this part here, around the partition shuffle? So we're sending K1 or K1 various times. Yeah? Seems a bit redundant, right? Because if we have a very common word like de, we could have, in a very large file, this could turn out to be de1, 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 and we could have thousands upon thousands of pairs that are just de1, 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 yeah? Or la1, 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 yeah? So that seems kind of inefficient. Maybe there's a way to optimize for that, right? So this is the idea of the combiner. So the idea of a combiner is that it's something like a mini reduce. Yeah, it's a reduce we apply before we shuffle the data over the network. So what happens is that we're going to define an intermediary phase before we send the data over the network. And what we're going to do intuitively is just sum the numbers before they go over the network. So here we have the result we saw before, but when we write them to the file, when we see in the same local file, we see K1, K1, K1 all together, the same word in one, we're going to sum them, yeah, just in that local part, yeah. And then we're going to continue the process exactly as before, but instead of sending lots of K1s in one batch, we're just going to have K2, or K how many times it appears, yeah. And then the rest of the output will be the same, except for in the reduce. Before I said we could apply a count or a sum. Which do we have to apply in the reduce now? So we could either count the number of values or sum the values. In the reduce now we only have one choice, which would be to sum. Yeah, if we count here we'll get 3, if we sum we'll get 4, right? We want to sum. Yeah. So if we sum here and we sum here, then the output will be the same. Yeah. So we can apply a combiner in some cases to initially reduce some values we see on the local side here to reduce the number of key value pairs we're going to work. So this can be a great optimization depending on the data. So the combiner sits between, again, somehow the partition and the shuffle. Yeah, so we can somehow already start to merge some of the data, and this leads to us having to send less data over the network, fewer pairs of keys and values. Yeah. So it's an important optimization. Okay, so we saw how to count words. Very, very nice. How often are we going to count words? Is this whole course about counting words? No. So we can see how we can use MapReduce maybe for some more complex tasks. So you get a job in a supermarket, and the supermarket boss wants to know, do we sell more in the morning hours or the evening hours? So the boss wants to do some analysis of which products do we sell more in the morning. We would expect maybe coffee might sell better in the morning, newspapers, whatever. And what do we sell more of in the evening hours? Maybe alcohol, wine, I'm not sure. Right? So let's take this example and let's see what data we have received. So what we have is basically 3 very, very large files. Could be TSV or CSV or whatever. They're already stored in HDFS, so they're already stored in a distributed file system. If not, you could upload them to the distributed file system. Let's say there's gigabytes of data in each one. Yeah. So we have these 3 files: a purchase file, a time file, and an item file. So CSV, TSV, some sort of table format. We have IDs for receipts and IDs for items. Yeah, in purchase. So this associates a receipt with a list of items, with one or more items. Then we have the time. We associate with each receipt one time. So a receipt ID can have multiple items. It can have one time. And then with each item, we associate a name and a price. And what we'd like, no, it's not by product, sorry. But what we'd like to know here is for each hour of the day, how much we sold. We'll see the product example later in the next class. So here we see the total amount of how much we sold of each product, right? So how are we going to compute the total sales per hour of the day? Yeah. So we could do this in SQL. You could try to load this into Postgres, but you're going to have a pretty tough time running this sort of query. Yeah. If you have like gigabytes, if you have hundreds of millions of lines and you try this in Postgres, you could be waiting a very, very long time. It might also just not work. So, but if you were to write it in Postgres, you could write it as an SQL query. So what joins would you need? Yeah, you would need to join purchase table with time on receipt ID. Yeah, and that will give you what items were purchased at what times. Yeah, and then you want to join that result with the item table and price. Yeah, you want to get the, so now you've got the item and the time from the first join, and then in the second join you want to get the price of the item. So then you have the price and the time. And then finally in SQL it would be a group by hour. Yeah, we're going to have to process that a little bit, but group by hour sum. Yeah. So we can do something similar in MapReduce. We can implement these functions, but we have to implement them in the MapReduce abstraction, right? So how does it look in MapReduce? I'll use my pointer here. Hopefully you can see it to indicate. So this is some syntax, some pseudocode for MapReduce. Yeah, this is not standard. This is something we use in this course. But so we're going to have 3 MapReduce jobs. This is the first one, and the first one relates to the join of purchase and time. Yep. So you're going to join on receipt ID. So we're going to need 2 maps because we have 2 input files. So we can have multiple maps, but we always have one reduce in a MapReduce task. Yep. So we need to have at least 1 map, but we can have multiple, and we have exactly 1 reduce in a MapReduce task. So the first map, we read from the first file, which is purchase, and we need to define, this is receipt ID, receipt item, sorry, these are the pairs RI, receipt and item are our pairs. What do we write out? For each input pair, we can write out 0 or many output pairs. In this case, we're just going to buffer, which means we just write receipt and item. Yeah, we don't do anything more than that. We read the time table, and for every pair of receipt and time that we read, we're going to output a receipt and the hour of the time. Yeah, so we're going to extract what hour of the day. So rather than 1653, we're going to put 1600. Yeah. Then in the reduce, we're going to automatically group all of the values with the same OR together. All of the values with the same receipt ID, which will give us a list of items and a time. Yeah. So when we do the reduce, the inputs will be from these maps. It will reduce what these maps produce here. We'll have, for each receipt, for each value of OR, we'll have a sequence of items, or it could be also a set. I guess the order could come in anything, but we'll have a list of items and 1 hour. Yeah. And then what do we want to output for this? For each receipt, we get a list of all the items in the hour. We're going to output a list of pairs of what item and the hour. We don't care about the receipt. Nobody cares about the receipt. We just wanted to create these pairs of item 1 hour, item 2 hour, item n hour. So for every item in a particular receipt, we output the item and the hour. Yep. Does that make sense? Okay. So 1 MapReduce job for a join. So we have a second MapReduce job for the second join. So the inputs this time will be the item. Yeah, so we're going to take we want the price information here, and we're going to find it based on the item ID. The second input would be from reduce 1. It will be these pairs of items and hours here. Yeah, so for every item and hour here, we're going to output item and hour here. Sorry, here for every input of item, name, and price, we're going to output just the item and the price. We don't care about the name. Yeah. So map 2, here we have for every item and hour, we're going to output a pair with item and hour. So we have our keys will be, in this case, the items. So for every item, we're going to have a list of all the values associated from any of the maps, which will be a price and an hour. A price and a list of hours, different times when that item was bought. Yeah. So we assume that each item has only 1 price. Yeah. So here for every item, we have a list of all of the hours in which it was bought, possibly repetitions as well. So we could have 6 o'clock several times, 7 o'clock several times. And then we have the price, right? So what we do here is we don't care about the item anymore. We just care about the hour and the price. Yeah, so we output pairs, which are what are the hours and what are the prices. So once we have all these pairs of hours and prices, the last thing to do is to have a last MapReduce job which does the group by count. Yeah. So what we're going to do here is for every hour price in the output of reduce 2, we're going to map to key values that have the hour as the key and the value, the price as the value. And then we're going to apply a reduce. In this case, we're going to define the reduce function as a sum of all the prices. So for each hour, we're going to have a list of all the prices of all the things that were bought that could be duplicated. And we're just going to sum all of those, and that gives us the sales per hour. So the key idea here is that if we want to do, for example, joins, we can do that in MapReduce using using 2 maps or multiple maps if we want. We can do a 3-way join by having 3 maps, for example. We can do group by operations. We can do aggregations. Here we're doing a sum, and so forth. So in MapReduce, we can do more advanced kinds of operations using this. Any questions or doubts about this? So we're doing something like an SQL query, but in a completely different framework. Yeah. So we'll talk a little bit more about that next time, the relation between this and SQL. But we see that we can implement stuff like this. And the idea again is, if this works in a relational database, fantastic. Do it in a relational database. But if it doesn't, it might be because you have too much data, for example, for one machine, or your relational database doesn't scale very well. In that case, you might need to move to something like MapReduce. Yeah. So this is somehow what all we're talking about here is somehow the last resort. If nothing else works, this is what you use. If something else works, if it works in memory, fantastic. Do it in memory. Do it in Python. Do it in a relational database. But when all of that stuff doesn't work, then you have a big data scenario. Yeah. So then you need to use something like MapReduce. So this is one possible solution in MapReduce because of we can change the order of joins and not affect the equivalence of a query. We could also do the joins in different orders, for example. So there's some other possible ways that would be similar. Okay, so now we have our distributed abstractions, we have our distributed file system, and we have our MapReduce function that we can add to this. Right? So what do we need to pass to this MapReduce framework? We need to pass a map function that tells us how to form the map keys and pairs. Keys and values pairs from our input. So what are the keys? What are the things we want to group by? Yeah. The reduce tells us for each key what function to apply to reduce all of its values. Yeah. So if we have an hour, like a time of the day, and we have a list of prices, we want to sum those prices, not count them. Yeah. We have our input file and our output file. So this is the MapReduce abstraction. So MapReduce, the benefit of this abstraction is that it's been implemented on top of the distributed file system. So it's been implemented on a distributed system. It takes care of fault tolerance, it takes care of communication machines, it takes care of load balancing, all of that stuff that would be very difficult to otherwise implement. So it takes care of a lot of the low-level implementation on thousands of machines, and it abstracts away details of fault tolerance, physical locations of machines, what are their IP addresses, which rack are they on. Don't need to care about any of that anymore. You don't need to care about adding or removing machines. It should be transparent. You can add and remove machines in. They will be used as they're needed. And load balancing. So it takes care of all these sorts of low-level details. So that gives people who work in Google, for example, time for more important things that you don't have to be worrying about these low-level details. I don't know why there's chests on the ceiling, and I don't know why it's 4 by 8. I don't know how that works. Yeah, so again, you're never going to use MapReduce. But the open source implementation of MapReduce is called Hadoop. Yeah, and Hadoop you can use. HDFS is the Hadoop distributed file system, so they come as a pair. So Hadoop is the open source version of MapReduce. It's used quite a lot in conjunction with HDFS for processing large amounts of data. So there's some, again, translations that in the client, in the Hadoop sector, we have a job tracker, which is this sort of node that coordinates what jobs are going on, what resources are allocated, or what job should be given to what machine. And then we have the job nodes that actually do the processing that's required. So the rest is material for the lab. So we'll see in the lab on Wednesday. We'll have a Hadoop lab. Yeah, so a problem to solve with Hadoop. There's a couple of caveats with the lab. One thing is that there's a lot of students in the course, and we have a very small, modest cluster. So it works okay, but it might require a little bit of patience. Yeah. So things might go on fire and so forth. So we're all going to be sharing one cluster that we have. The cluster is not super powerful, but with some patience and some instructions and some care from you as well, it should work out okay. So we'll talk about that on Wednesday. So see you on Wednesday. Yep. Any questions? Comments? No? Okay, so see you on Wednesday.